Okay, so for this new unit, we're going to move on from the derivative as a concept of slope and now think of the derivative as its own function. So to start, we're going to graph some original equations. So open to page 3. We're going to graph y equals 3. So that's everywhere y is 3. Connect the dots. We have this horizontal line. And so now for this one, we can just look, and I want to know what the derivative is at all of these points. So over here at -3, the derivative is 0. At -2, the slope is still 0. -1, still 0. The slope everywhere is 0. So now to graph the derivative function, we're going to plot all these coordinates, -3, 0, -2, 0, -1, 0, and keep going. Connect the dots. And now we have a new function graphed. And so the derivative function everywhere is y prime equals 0. All right, let's try the same thing for the equation y equals -3. Let's graph y equals -3. The derivative everywhere of this graph is still 0. So we're going to plot those points. Connect the dots. And the equation of the new graph, the derivative graph we just graphed, f prime of x is 0. I promise they won't all be so straightforward. Okay, let's graph y equals x. Y equals x is 0, 0, 1, 1, 2, 2, 3, 3, -1, -1, -2, -2. All right, let's think of the slope at all of these points. It's a linear equation, so we could even look and see what value is in the slope location, and that's a value of 1. The slope everywhere of this line is 1. You can count it, rise over run, rise over run. So now I'm going to plot -3, 1, -2, 1, -1, 1, and so on, and connect the dots. And now this derivative, f prime of x, equation is 1. Everywhere the y value is 1. All right, let's graph number 4. You could use your graphing calculator. I'm going to use the slope and the y-intercept. So we're going to start at -1 for the y-intercept. And the slope is -2. So I'm going to go down 2 and to the right 1. Or we could go up 2 and to the left 1. Up 2 and to the left 1. Connect the dots. And the tangent line everywhere, the slope at all of these points is -2. You can also see that from the linear equation. And so this derivative function is f prime of x is -2. All right, now we're going to get to some more exciting ones. Y equals the negative absolute value of x. If you want to graph this in your calculator, the absolute value is in the math menu, arrow over to num, and choice 1 is ABS. So negative absolute value of x, let's go -3. Absolute value of -3 is +3, but with a negative coefficient. We're at -3. Negative 2 has an absolute value of positive 2, but times the negative coefficient. Negative 1, 0. And it's going to give you this V shape. We can graph it in the calculator. Math, num, ABS, x. I forgot my leading coefficient of negative 1, so I'll put it at the end. Oh, my window's messed up. All right, zoom 6. So there's that V shape. You could go second table. I see all the inputs with outputs. So now let's do our derivative. The slope over here at negative 3, this piece of the function has a positive slope, right? It's going up 1 over 1. So these points would have a slope of positive 1. Over here on the positive x values, this is down 1, right 1. So these are negative 1 slopes. But something special is happening here at x equals 0. It's a sharp point. The derivative does not exist at a sharp point. It's because the limit of slope on the left and the limit of slope on the right are not approaching the same value. So we're going to have a discontinuity in this derivative function. So let's graph negative 3, 1, negative 2, 1, negative 1, 1, 1. All right, so then we've got these negatives. And so what's happening is I still need to include derivative values really, really close to 0, but not quite 0. So this horizontal segment will stop when x is 0 with an open circle. So what I highlighted on my original graph in green, that's this section right here in green. So we need to get really, really close to the undefined derivative value, but not quite there. And we're going to show that with the open circle. So this derivative function has a jump discontinuity. We're not going to write the equation for that. We'll just leave the graph as it is. All right, let's try number 6. This one we'll just graph in the calculator. Okay, so remember, this is the original function we're graphing. 2 absolute value, absolute value, x minus 1. I'm just going to go to my table. All right, so this is the original function's y values. Negative 3, 8. Well, that's off this grid, so okay, that's negative. All right, let's do negative 1, 4. 0, 2, 1, 0, 2, 2, and 3, 4. So we have that same V shape, but now with the transformations, it's shifted to the right 1 and a vertical dilation of 2. All right, so for the derivatives, the sharp point is here at 1, so that derivative does not exist. To the right of 1, it looks like the slope, let's go from 1 to 2. If we're going to count up 2 and over 1, that's that dilation number. That's the slope on the positive side. On the left, it looks like it's negative 2. All right, so we've got negative 3, negative 2, negative 2, negative 2. Negative 2 does not exist at 1. And then does not exist at 1, but positive 2, positive 2, positive 2. And we've got another jump discontinuity derivative graph. And we can see that vertical stretch of 2 even in the derivative. So far, all of these graphs have had straight linear pieces to them. It was either a straight line or these absolute value have 2 parts that are just straight. So now we're going to get to graphs that are more curved, like y equals x squared. So you've got 0, 0, 1, 1, 2, 4. So we're going to get this U shape now. And to get the derivative values, we could draw tangent lines at all the x's. I don't recommend this. I'll just show you what it would look like. So we can draw a tangent line at -3. Oh, I didn't really line that up very well. And count the slope, and then we could draw a tangent line at -2. I missed. And count the slope, and then we could draw a tangent line at 0, and count the, well, that blends in. And count the slope. Then we could draw a tangent line at +1. Okay, that's going to be messy, and it's all estimates, and that's just not, we're not going to do that. Instead, the calculator will calculate derivative values for us. Yay! Here are the calculator steps. Pause the video and write them down now, and then we're going to do them together. All right, so the first step is to put your function in y1, so x squared. And then exit to the calculation screen. So we want to go back to like the main screen where you just calculate arithmetic. So we're going to go second mode. Press math, and choice number 8 is NDeriv. Now, old calculators do this in one way, newer calculators do it in a different way, so I will show you both. I'm going to first show you the new calculator way. Okay, go back math, choice 8, and we get this notation of D and then all these squares. So the first square where my little a is blinking needs to be an x, because this is saying take the derivative with respect to x. And then we need to tell the calculator of what function. So in the parentheses goes the function. I like to use the notation of y1 because then I don't have to retype the function every time. So I'm going to go to vars, yvars, function, y1. And then we have to tell the calculator at what x value. So I'm going to say -3. So the derivative at -3 is -6. Oops. Oh, there's my kids. They're going to hate that that's in the video. Oops. Okay. Now we're going to go second, enter, and it brings back up what I typed. So I'm going to back arrow and change this to -2. Enter. Second, enter, change it to -1. Enter. And you can see we've got now 2 more derivative values, -4, -2. We're going to keep going. Second, enter, 0. And now I see a pattern, so I'll just count it out, 2, 4, 6. The old calculator way, if you have a classic calculator, when you do math 8, you don't get those squares. So our order of symbols needs to be y1, comma, x, comma, the number. So we're going to go vars, yvars, y1, comma is above the 7, x, comma, and then I'll just continue with the positives to show you I had them right. Ooh, not 21. So the slope at 1 is 2. Now I go second, enter. Slope at 2 is 4. Second, enter. Slope at 3 is 6. All right, so now let's plot our points. -2, -4, -1, -2, 0, 0, 1, 2. Connect the dots. And this derivative function, it's a line, so the slope is 2. So we got 2x plus a y-intercept of 0. All right, let's do another one. Let's graph -x plus 2 squared. I'm going to use transformations. You use your calculator if you want. Follow along with me with transformations. This goes left 2, reflected with the negative in the front, and it's a parabola. All right, now let's fill in our y values. We're going to go back and do n deriv. You decide what mode your calculator's in, if it's old versus new. I have to change my y equals. Now the best part, because I used y1 here, if I do second enter, and see how now it still says y1, this is going to reference my new function that I typed into y1. So I don't have to deal with the math 8 all over again. So that's a derivative of 2. Second enter. That's a derivative of 0. All right, if you're a math print person, one more time for you. Put my function in y1, second mode, math, choice 8. X goes in the bottom. Whoops. Y1 goes in the parentheses. The x value we want the derivative at goes at the bottom. Counts by 2's again. All right, -3, 2. All right, and this derivative function has a slope of -2x, and then the y-intercept -4. Okay. So taking this a step further, now we're just going to, in general, analyze functions. What x values are the following functions not differentiable? That means no derivative, or the derivative does not exist. So let's do it that y prime does not exist, which means a sharp point. Notice we've got all these absolute value functions here. So we're going to make a sketch. Ooh. Absolute value of x, x plus 3. Okay. The absolute value of x has a vertex at 0. So this graph or this function is not differentiable at x equals 0 because that is where the sharp point is located. For b, this absolute value function moves to the left, -3. I will prove it to you in my calculator in just a minute. So this equation is not differentiable at x equals -3. There it is. All right, last one. We got 3x minus 6. All right, that went to the right too. Has that dilation on it. So this function is not differentiable where x is 2. All right, number 11. Find the equation of the tangent line, sketch a graph. I'm going to teach you one more thing in the calculator today. We're going to go to y equals. Let's input that function. Did I get it right? Yes. All right, hit graph. Now, our calculators will also draw the tangent line. So if I see the draw right above program, so we do second program. Number 5 is tangent line. But then I have to tell the calculator at what x value. So I'm going to press 2, enter. At the bottom, it tells us the entire equation of the tangent line and gives us the sketch. So I'm going to sketch this parabola. Kind of missed. Okay, the tangent line at 2 is over here. Also missed. And then the equation y equals 2x minus 2. All right, let's try B. Second program, draw tangent, so number 5. The x is 7. Enter. Now we've got all these decimals. Let's figure out what those are. So I'm going to go to the main calculate screen and type 0.166666666. So just a whole bunch of them. And then math, enter, enter. That's 1/6, 1.8, and then a whole bunch of 3s. Math, enter, enter. Okay, so we got our sketch. We've got our tangent line. And the derivative, the tangent line equation is y equals 1/6 x plus 11/6. So by using the decimals from the draw tangent and then the change your answer to a fraction in the math menu, we can get a nice equation. All right, one more. Anytime you have a denominator that's not a single term or a numerator, you need to put that part in parentheses, just like I did here. Graph, second program, number 5 at 2, enter. All right, for the tangent line, you have to use your brain. You are smarter than these calculators that are just estimating. This equation is y equals -1x plus 3. Do not, on an assessment, give me all these zeros. And if it says 2.999999876, you also round that to 3. All right, last but not least, we have a function and we want the rate of change at 3 minutes. Okay, so in the last unit, we were busy finding points really, really close on the left and really, really close on the right, and then finding the slope really, really close on the left and the slope really, really close on the right. And now we can just use nDeriv. Depending on your calculator, you fill in one of these blanks. So if I have the older calculator, this will be y1, x, 3. Newer calculator, you got the x, the y1, and the 3. And our rate of change is going to be milligrams per minute. And now we're going to use the calculator to get the derivative, that instant rate of change. So let's put the function in y1, 25 e to the negative 0.2x. There's no t variable when you're in regular mode in the calculator, so you have to use the x button. Second quit, we're going to go back to the main calculate screen. Math, choice 8 is n-deriv, x, whoop, y1, 3. And then let me do the other way for you classic calculator people. Math 8. Oh, wait, let me show. The equation's still in y equals. Vars, y1, comma, x, comma, 3. Same answer. So the answer is 2.7. Oh, it doesn't tell us decimals. All right, let's just do 2.74, negative 2.74 milligrams per minute. All right, your practice is page 9 through 11. Make sure to check your answers in Drive.